Hey, welcome back to Calculus. In this video lecture, we're going to be taking a look at material from section 2.7 about the derivative at a point. We're going to cover section 2.7 over 2 days this week, not just one. So there's going to be a day 2 of section 2.7 following this one. And I'm also going to make 2 videos for this day 1. I'm going to make this one kind of short and focused. Now you can see the objectives there. I want to tell you what I mean by the derivative of a point, so make our main definition. This is a central notion to our course, so it's super important to digest this material deeply. Then I'm going to do a couple of computations and try to illustrate the relationship between it and tangent slopes and velocity. It's kind of what motivated us all to think about limits in this whole chapter. The second video for this section 7, day 1, I'll just do several more examples. In this one, I'm just going to do 2 examples, keep the video short and focused on the definition, and then I'll make a follow-up video in which I produce, I think, probably maybe 3 more examples to give you lots of things to refer to as you work through the problems in the text. More than ever, I mean, every section, it's important that you do those drill skill problems out of the textbook homework. This one in particular, you want to practice these computations until you have a lot of confidence in them. Okay, so let's get going here. Said what the objectives were. Let's try to motivate the lecture. So, well, we were motivated by this whole subject of limits by something called the tangent and velocity problems. Remember the tangent and velocity problems? Tangent line to a curve, or the instantaneous velocity of an object. Both of those problems led us to consider the following limit. Both problems led us to consider the limits where we looked at a change in the output of the function. So we have 2 values, a and x. I'm going to use this graph to kind of walk us through this definition, or this limit. So I've got a graph, y equals f of x. Maybe it's just some graph. Maybe it's the position function of an object. I've got a point on it, a comma f of a. And then I look at the so-called secant slope. The secant slope between the point a comma f of a and x comma f of x is given by, well, the change in y over change in x. So I take my f of x minus my f of a, that's my change in y coordinates, yeah? And then I have to divide that by my x minus a, my change in x coordinates. That's a secant slope in general. If f is a position function, I'd call that the average velocity over the time interval from a to x. So the tangent and velocity problems led us to considering these limits of change in f over change in x, change in output over change in input. All right, so before we look at the main definition down here, I'm going to write it in 2 different kind of, I don't know, coordinates. I'm going to make a variable switch because depending on the computation, it can be easier to use one of these things than the other. So I'm going to call in this picture the distance between x and a, I'm going to call it a variable h. Yeah, delta x is another name you might see in other books, but our book calls it h, so I'll use the same notation. So over here, I'm algebraically writing down what I mean. H is x minus a. Well, and of course, that's algebraically equivalent to just saying that x is a plus h. You can just add a to both sides, okay? But h is the distance between x and a. And the kind of fundamental observation I want you to make with me is that as x approaches a, h will approach 0, and vice versa. That's what my little symbol here means. It means that if this happens, so does the second condition, and vice versa. So just imagine in this picture, if you could move this x coordinate closer to a, well, that's simultaneously going to be shrinking this variable h. Or conversely, if you shrunk that variable h, a is not going to move, so that would force x to approach a. Okay, that's all I mean by this. So let's look at the main definition here. Put my applications of it where you can see them too. So we're going to call this limit, this thing that we're used to, this limit of secant slopes, this limit of average velocities. I'm going to call it the derivative of f. And then there's a lot of prepositions here because f has an input variable called x, and we're doing this derivative at a number called a. So the prepositions, it's the derivative of f, that's the short version of it, but it's with respect to x. So that's just specifying what the input variable is. And then we have to say at x equals a. It's where we're computing this limit, okay? So that's why there's so much terminology. It's the derivative of f, but we say with respect to what input variable and where are we taking this derivative. And what is the derivative? It's a number. What number is it? Well, it's this limit. It's the limit of those average velocities. And we're going to denote this number in the following way. I'm going to write f of a with a tick mark up there. It's called a prime. You read this out loud on the telephone, f prime of a. Yeah, and why do I want to denote it like that? I can't denote this number by f of a. F of a is already meaning something, but I don't want to invent a whole bunch of notation. So this prime is just reminding me, well, it's a number that depends on f and a. How does it depend on it? It's this value. You compute this limit. It's called the derivative. If we make that variable switch, can you still see it up here? Maybe I can try to put it back. If we let h equal x minus a, sorry, I'm stumbling, then x is equal to a plus h. So if I replace this x in this formula with a plus h, it looks like that. Yeah. F of a is f of a. I'm not doing anything there. And we wrote above that x minus a is h. And we said that as x goes to a, h will go to 0 and vice versa. So this equality is really just a variable switch. Those two limits are equal by definition. And why have both of them? Well, sometimes one of them is easier than the other one to use in a given competition. So we're not going to throw either one of them away. All right, so you might want to pause for a second and think about this. Let me put the applications back while you're thinking that, what is this number? What is this f prime of a? Why do we care about it? Well, it has some already important applications for us. F prime of a, the derivative at a, it's the slope of the tangent line to the graph at a comma f of a. That's what that number means in one application. If f is a position function, then f prime of a is the instantaneous velocity. When time, I'm calling the variable t in the position function. I'd call this the derivative with respect to t. At t equals a, and it represents instantaneous velocity. So this thing has two important applications already, and it'll have many, many more. This derivative is quite literally the subject. Sometimes people call a first semester calculus course differential calculus, and differential is derived, slight pun intended, from the word derivative. Okay, let's look at an example. You might have to refer back to this, or you've got your book open. I've got this definition where I can see it, but you're not going to be able to see it on my screen as I do this example. So the example is, given f of x equals x squared, find f prime of 2. Yeah, so this is another way of saying compute the derivative of f with respect to x at x equals 2. That's what we want to do. Compute the derivative of f with respect to x at x equals 2. Or more briefly, find f prime of 2. All right, I'm going to scroll back, sorry. I'm going to use this formulation for this derivative. I'm going to take the limit as x approaches 2 of f of x minus f of 2 over x minus 2. So you see the role that the 2 is playing. It's my a value. All right, so maybe I can try to leave that visible as I write the first line here. So this is a definition that you want to internalize, burn into your memory as soon as you possibly can. That f prime of 2, this first part will be the same for any function. It's just using the definition. So we're going to take the limit as x approaches, in this case, 2 of f of x minus f of 2 over x minus 2. Okay, now I'm going to scroll and give myself some room to work here. So I'm going to remember what f of x is here. I'm going to keep writing this limit notation until we take the limit. It's very important to use the notation properly. F of x was equal to x squared. F of 2 is 2 squared, that's 4. X minus 2 is just going along for the ride. And now we are back in what we were talking about earlier in chapter 2. I need to take a limit, both the numerator and the denominator. Remember, my advice is when you're taking a limit, you look at the denominator first, it goes to 0. So then you ask yourself, well, what about the numerator? The numerator is also approaching 0 as x approaches 2. Right? 4 minus 4 is 0. So when that happens for a rational function, we can factor. We got to factor this expression. So I'm going to write my limit notation again carefully, and I'm going to factor that numerator into x minus 2 times x plus 2, difference of squares. Yeah, and now as long as x isn't equal to 2, then I can cancel those factors. And I don't mind restricting x to not equal 2, because when I take a limit at 2, I don't need the value of x to be able to equal 2. So our property from the limit section says that this limit is going to be the same as the limit as x plus 2, as x approaches 2. And as x approaches 2, x plus 2 approaches 2 plus 2. It's a lot of 2's. That's 4. All right, so what's my summary? F prime of 2, just to get used to the language again, the derivative of f of x with respect to x when x is equal to 2 is 4. So there you go. We've computed a derivative together. The derivative of that function at 2, f prime of 2 is equal to 4. Cool. It's kind of a follow-up question, a second example. Can we keep that in mind? The f prime of 2 is 4. My second example is find the equation of the tangent line. Equation of the tangent line to f of x equals x squared at the point 2 comma f of 2. Yeah. So what is the equation of the tangent line? So what do you need to find the equation of a tangent line? Well, you need a point. Find an equation of a line, you always need a point. We're given the point. It's 2 comma f of 2. F of x is x squared, so f of 2 is 4. Yeah, and we also need the slope. Need the slope. Well, the slope of the tangent line, that's f prime of 2. Lucky us, we've just computed it. It's also 4. So my second example, I'm really just asking you, can you find the equation of a line through the point 2 comma 4 that has slope 4? Yeah, sure you can. You could find the equation of a line given a point and the slope. So let's use the point slope form. Point slope form of a line, you take y, subtract the y coordinate that's known to be on the line, set that equal to the slope 4 times x minus the x coordinate of the point that's known to be on the line. In some sense, I'm done, but I like to put my lines in the form of y equals mx plus b. So let's just do a teeny little bit of algebra here. That's 4x minus 8 on the right-hand side. And then if we add 4 to both sides, negative 8 plus 4 is negative 4. So that should be the equation of our tangent line. This is the tangent line to f of x equals x squared at the point 2 comma 4. And if that's right, if we graphed the function x squared and this line y equals 4x minus 4 on the same set of axes, it should look tangent. Let's do it real quick. I'm going to take us over to Desmos window. Can pop over there pretty quickly. I've got it ready and waiting for us here. So here's our usual Desmos window, and how to graph x squared. Well, you just type x squared. There's the usual parabola. It's sort of first nonlinear function you probably ever learned about. And then I've got this equation of the tangent line, 4x minus 4. So pop that in there. It's going to draw it in blue, and then you can shift around and look. But yeah, it looks right to me. That line looks tangent to the curve. They're both passing through the point 2 comma 4. If you want to highlight that point, you can add it in your Desmos window and put a label on it. So there's your point 2 comma 4. And then if I zoom in on this thing, oops, that's the wrong way. I can see that, yeah, that looks pretty tangent to me. If the line is tangent, nearby the point of tangency, the curve and the line should become indistinguishable. That's kind of a feature of what this notion of derivative, we'll talk extensively about that in section 2.8. But yeah, I hope you do this in all your examples. You know, you find an equation of a tangent line, you've got Desmos sitting right there. It takes 30 seconds to graph the function. Check it out. Graph the function, graph the tangent line. You can catch errors that way. Say, for example, you're taking a midterm exam and you're asked to find the equation of a tangent line and you want to know, is it right before I submit it? Well, check out a graph. You know, you can determine if it's right or not. Cool. All right, let's come back to the whiteboard. I'm going to do one more example and then I'm going to call it for this one, trying to keep this video a little bit on the shorter side. I'm going to just make a second video with nothing but examples in it. Just trying to do that to help it make it easier for you to focus. For me, it's very difficult to focus on videos that are 30, 40, 50 minutes long when it's easier for me to have something that's shorter that I know. Okay, so here's my third example. I'm given that an object moves t cubed meters in t seconds. So this is a position function. Anytime somebody's telling me about how far something moves in some amount of time, it's a position function. All right, and then what's the question? The question is, well, find the velocity, that's the key word, of this object when t is equal to 1. Find the velocity of this object when t is equal to 1. So translating it, we know that and by the way, by velocity at a point, I always mean instantaneous velocity. So translating it, what were we asked to do? We're asked to find the derivative of this function f at 1. Find f prime of 1. All right? So I'm going to use the alternate version of the derivative. Here, let me see if I can scroll back up kind of quickly. For this particular computation, I said that sometimes it's easier to use this alternate definition. I'm going to use it over here, this h. Why? Well, this is a cubing function. So if you think ahead a little bit without writing it, if we use this version of it over here, we're going to have like x cubed minus 1 cubed, and we'll have to factor that. Factoring cubics is a little bit harder. Over in this side, we'll just have 1 plus h cubed minus 1. And it's easier to cube out something than it is to factor it. So that was sort of a poor explanation, I think, but that's why I'm going to use this alternative definition. The short story is that sometimes the algebra is easier in one of these forms than the other. How do you know which? Well, you don't. At the beginning, you have to gain experience. Yeah, so I've computed quite a few derivatives like this, and I happen to know that if the power on the exponent is, the power of x is higher than 2, it can be hard to factor, so I like this alternative definition. All right, so let's see if I can go back down and find our workspace and continuing along. So you were just looking at that definition. You can pause and look at it again. F prime of 1, I'm going to write, is the limit as h goes to 0. When you use this alternative definition, h is always going to 0 because it's the distance between your point and your variable. All right, my variable here is called t, so I'm taking the limit as h goes to 0, and then how does the definition work? I'm supposed to take f of 1 plus h minus f of 1 and divide it by h. That's the definition of the derivative. Something very important to know. I'm using the alternate definition. Good. So now let's start remembering what this function f is. This function is the cubing function. So I need to take that 1 plus h and cube it. I need to take 1 and cube it and divide by h. All right, so using kind of a FOIL, if you like, or expanding out the terms, I'm just going to do it here on the fly. You can come to an office hour if you want to talk to me about it or look at an algebra review. But when you cube 1 plus h, you're going to get 1 as the one of the terms. And then you're going to get 3 times 1 squared times h. And then you're going to get 3 times 1 times h squared. And then you'd get an h cubed. All right, so just to give you a color coding, this 1 plus h cubed expands out into those things. Maybe come to my office hour and we can talk about how to do that. We can talk about something really cool called Pascal's triangle too, if you've never seen it. It's a neat way to expand those things. But to keep this video short, I'm just going to keep going. So now in my numerator there, I can see that this 1 and that minus 1 cancel additively. And then it's an important observation. Every other term has an h in it. Yeah, so I'm going to factor that h out, and I'm going to write this explicitly to give you a good roadmap for this kind of algebra. I apologize if I'm going too slow for your algebraic ability, but it doesn't, you can just speed up if all of this makes sense. So if I factor an h out of that numerator, yeah, once I do that, then I can see that there's a multiplicative cancellation. That's why we couldn't just plug h in equal to 0, but now we can, because we've canceled the h that was causing the 0 in the denominator to be gone. So that cancellation was valid as long as h isn't 0, which it's not because we're taking the limit towards 0. So we're taking now the limit as h goes to 0 of 3 plus 3h plus h squared. All right, and you can see that these terms with h's in them are going to vanish. They're all going to be 0. So what do we end up getting for the limit? We end up getting 3. So f prime of 1 is 3. Let's remember what the original question was. The original question was find the velocity of the object when t is 1. So I want to answer that the velocity is 3. So the velocity when t is equal to 1 is 3. But in a context like this, you definitely want to put the units in. right? So 3 watts. Sorry for all the scrolling, but we were measuring our distance in meters and our time is in seconds. So this is actually kind of a really cool thing about these notations that we're using. It tells you what the units are. This difference in the numerator is a difference in meters. Yeah, the difference in the denominator is a difference in seconds. Well, if you divide meters by seconds, you get meters per second. So my better answer than just saying 3, I want to say it's 3 meters per second. That's the velocity of that thing. Okay, so thanks for listening. I'm going to keep this one short and you can watch the next video. I hope it's about 15 minutes long, in which I try to calculate about 3 more derivatives, showing you some variations on the theme. Thanks.